Yeah, thank you for coming to my talk. So this is a joint work with Itai Ashlagi from Stanford and Itai Gurvich from Northwestern. So there are numerous marketplaces such as kidney exchange, labor markets, and logistics, which are centralized and dynamic. And in such dynamic markets, agents or supply and demand arrive gradually over time. And these can match with one another, where either there's a social planner that has a full control over conducting these matches, or the planner recommends which matches to perform. And the social planner may have different objectives, such as maximizing the total number of matches or the total match value, or minimizing waiting times or holding costs, where the planner may optimize these objectives over short or long term. And the fundamental question that the planner needs to answer is that who to match and when to match. And the main focus of this talk is the following inherent trade-off that arises in dynamic matching markets, which is between short and long-term objectives. And one can summarize this trade-off with the following simple question: do you match now or later? So on one hand, one may delay match decisions to increase match opportunities to generate high-value match, but this, by definition, inevitably compromises short-term objectives, and one may also match more frequently to maximize short-term objectives. So now let me elaborate more on this trade-off with a motivating example. So our work is mainly motivated by kidney exchange marketplaces, where kidney exchange platforms enable incompatible patient-donor pairs to swap donors. So on the left, there is an example of a two-way match between two incompatible patient-donor pairs. And in a similar fashion, we can also have multi-way matches, as shown on the right, where three patient-donor pairs are in a single match. And one key property of kidney exchange marketplaces is that different matches yield different life years from transplants, where these life years are predicted based on recipient's age, history of diseases, time on dialysis therapy, and so on. And in practice, we observe this trade-off between kidney exchange platforms, mostly in Europe and the US. So the national kidney registries in the Netherlands, UK, Canada, and Australia delay match decisions to thicken the market so that they can arrange these exchanges that yield more life years from transplants. As you see in this figure, these platforms wait 3 to 4 months before forming matches and clearing the market. In contrast, programs in the United States, such as National Kidney Registry, have gradually moved towards daily matching. So one reason is that many patient donor pairs are listed in multiple registries. So this creates a competition that drives these platforms to look for matches more frequently. Another reason is that some patients may no longer receive a kidney due to deteriorating health, and delaying match decisions may hurt such patients. And this practice actually raised concerns that matching frequently may harm efficiency, because the more frequent the match runs, the less optimization can contribute to increase the transplant opportunities. And practitioners suggest that dynamic optimization methods can allow these platforms to run frequent matches without compromising the quality of transplants. And this is sort of the part of the motivation to our work. Okay, so following these trade-off issues that we see in practice, our main goal in this work to understand this trade-off and quantify the value of delay. And to that end, I will be focusing on centralized dynamic match markets, where the planner is interested in maximizing the total match value. And I'll study a simple model that captures the key properties of dynamic match markets, which are stochasticity, heterogeneity, and the fact that the market is not necessarily two-sided. That is, I want to capture the fact that agent arrivals are stochastic and agent types and match values are heterogeneous. I also want to capture the fact that multi-way matches are possible. Recall that in kidney exchange, we can have a match between more than two patient-donor pairs, or for example, in ride-sharing, you can pool passengers. And hopefully, we'll achieve our research objectives by studying the following question: can we nearly maximize the total match value simultaneously at all times? So note that if I can positively answer this question, this will essentially imply that this trade-off between short and long-term objectives is essentially moot. So let's get started with the model. So there's a finite set of agent types A and a set of matches M. And A of M is the set of agent types participating in match M. And the network topology is specified by the matching matrix capital M, which is basically an incidence matrix. And I'm going to say that a matching network is two-way if all matches include exactly two agent types. And it is multi-way otherwise. Okay. So on the left, there is a multi-way network with 7 agent types or queues and 4 possible matches, where match 1 includes 4 agent types, which is the set A of 1 below. And on the right, there is an example of a 2-way network where its matching matrix capital M is indicated below. So what are the dynamics? We'll consider a finite horizon, discrete time dynamics, where each time period, there is 1 agent arrival. And at each time period, an arriving agent is type I, which also means that this agent joins Qi with probability lambda I. I will assume no departures. That is, these agents are infinitely patient. And I'm happy to talk offline about the case when we allow departures. And if we perform match M once, I generate this strictly positive match value Rm, okay? And as you notice in the figures, I indicate the arrival probabilities on the Q vertices and match values on the match vertices as shown in the figure. So to illustrate the dynamics quickly, let's say there are 3 agents arriving to first one to Q1, second one to Q3, and next one to Q2. So now as a planner, you can either perform match 1 or match 2, or you may not want to perform match 2 to possibly perform match 3 in the future if there's some arrival to Q4, okay? And let's say you decide to perform match 2, then these agents leave the market, and the planner collects this match value R2, okay? So the matching policy or control then simply decides when and what to match. And let's denote the counting process by DMT, which tracks how many times match M is performed by time t, okay? So now let me formalize our optimality notion. So the expected total value generated by a policy D at time t is denoted by R dt, and it's simply the expectation of the inner product between the match value vector R and the counting process vector dt, okay? And our benchmark is called the Hindsight upper bound, which can be interpreted as the performance of the no-regret planner at any time period, where this bound is the best possible total value at any given time t, okay? And I will denote this upper bound by R star t. And this bound is simply attained by performing the best set of matches at time t, by solving this simple linear program, where AT on the right-hand side is the number of arrivals vector, okay? And we say that a policy D is Hindsight optimal if for all t, the gap between this Hindsight upper bound R star t and the performance of the policy R dt is constant that does not grow with time. So I want to quickly note that this is a very strong optimality condition. And if a policy is Hindsight optimal, then it's also nearly optimal across criteria. Like the policy is also optimal in the long run average sense. And you can also interpret this as a Hindsight optimal policy makes a finite number of mistakes, no matter if your time horizon is 1,000 time units or 1,000,000 time units, okay? And we'll see what I mean by a mistake later on. So now let me define the static planning problem, which is an important linear program that will guide us when we will design our matching policies. So this linear program can be seen as a first-order proxy for the Hindsight upper bound, where we completely ignore stochasticity and optimize the first-order matching rates. And given an optimal solution, Z star and S star, note that Z star counts, it corresponds to the vector that indicates how many times I conduct each match under the optimal solution. And the slack variables, S stars, indicate the leftovers at each Q after we perform the optimal solution. So based on this optimal solution, I will be defining these 4 sets where M plus is the set of active matches, where these matches are used under the optimal solution. And then M0 is the set of redundant matches, where these matches are not used under the optimal solution. I'll similarly define Q plus, which is the set of under-demanded agent types, or Qs, because after we conduct the optimal solution, there are leftovers in these Qs. That's why they're under-demanded. And finally, I think the most important one, we define the set Q0, which is the set of over-demanded Qs because they're emptied under the optimal solution. And intuitively, we expect good policies to act accordingly. What I mean by that is that over-demanded Qs should be emptied in the dynamic system, and the redundant matches should be used rarely, if at all. So now I want to give you an example to illustrate what kind of results one can expect to achieve Hindsight optimality. So in this multi-way network, what I would like to argue is that no greedy policy is Hindsight optimal, where greedy policies are those that perform a match whenever possible. So here, the highest value match 1 with value 100 requires all these queues 6, 1, 2, and 4 to be non-empty at the same time, where these queues are indicated with these arrows. But under any greedy policy, we won't be able to perform match 1 sufficiently enough, because these agents actually disappear before they can be used for this highest value match 1 under any greedy policy. For example, Q4 with the rival probability of 8 lambda will be emptied after some initial transient horizon by Q5 with the higher arrival probability of 16 lambda. So in some sense, match 1 here introduces a complementarity, and after some initial transient horizon, the state of the market will look like this. So this shows that we need to delay match decisions in multi-way networks to achieve Hindsight optimality. And as we're going to argue later in the talk, this delay also needs to be carefully chosen. So now I'm ready to impose the main assumption on the network, which is the general position condition. And actually, we show that this is a necessary condition to achieve Hindsight optimality. So recall this static planning problem. And now I say that the network satisfies the general position condition, or GP in short, if the static planning problem has a unique non-degenerate optimal solution. And this is rather a weak requirement. It can be shown that both uniqueness and non-degeneracy can be satisfied with small perturbations. And one other interpretation of this condition in queuing language is that this condition means that the network is actually overloaded. That is, not all inputs can be served. Okay. Again, recall these two sets that I defined, M plus and Q plus. Now I'm defining the general position gap, epsilon, which is the minimum of ZM star and SJ star, where the minimums are taken over the sets M plus and Q plus. So you can just think this quantity epsilon as an indicator of the minimal basic feasible activity in the optimal basis. And this quantity will play a key role in the characterization of the constant regret. And this quantity basically captures the imbalance in the network. So intuitively, the higher the imbalance between the rival probabilities, the higher the general position gap epsilon. So now I'm ready to present the first result. I'm actually not going to go over the details, but what this result basically states is that in multi-way networks, there exists a simple batching policy that is Hindsight optimal. And this policy simply acts in decision epochs, and between decision epochs, it waits for market to thicken, and then performs the best set of matches at each decision epoch. And this policy achieves constant regret. It's Hindsight optimal, where the scaling of this constant regret is given by 1 over epsilon. And this is the best possible scaling you can get thanks to the second part of the result. But this result now raises an actual question, which is batching necessary for two-way networks? So recall that batching was necessary in multi-way networks due to these natural complementarities that were observed in the previous example. But maybe we can get rid of these in two-way networks. And it's natural to ask, are there any greedy policies that are Hindsight optimal in two-way networks? And the answer will be yes. So now let me define two greedy policies. So the first policy is a slight variation of the greedy longest queue policy. That is, at any time period, if feasible, the arriving agent is matched with its longest over-demanded neighbor, where recall that Q0 was the set of empty queues based on the static planning problem. Also note that since we are in the world of two-way networks now, I simplified the representation of networks, where now instead of these square nodes representing matches, now I replace them with the edges. So note that this longest queue policy is clearly a state-dependent policy. But in practice, state-independent policies are also greatly appealing, and they have a huge importance in applications like kidney exchange. And our second greedy policy is a state-independent policy, and it's called the greedy static priority policy, which is at any time period, if feasible, we perform the highest priority match based on this bijective mapping from the set of active matches to itself. So such a policy is very practical to implement, since basically all you need to do is to solve the static planning problem, come up with this ranking. So basically you design a menu, which gives you a ranking over these non-redundant matches, and you just follow this ranking throughout the horizon without making any additional optimization. So now I'm going to present two results regarding hindsight optimality on two-way matching networks. So the first theorem states that under the general position condition, which was a necessary condition, the greedy longest queue policy is hindsight optimal for any two-way network. Again, with the optimal scaling, 1 over epsilon, where the regret is also of the order of 1 over epsilon. If this two-way network is acyclic, that is cycle-free, then there exists a greedy static priority policy that is also hindsight optimal. So note that the longest queue policy achieves the optimal scaling for regret, whereas we couldn't establish the same scaling under the priority policy, so it's an open question. And finally, let me quickly mention how one determines this priority order if we have a two-way network, which is acyclic. So what we are able to show is that when G is two-way and acyclic, then any component after you remove all the redundant matches from the network has exactly one under demanded agent type. And the resulting residual graph is consisting of components that look like this network, where there is a single non-empty queue based on the static planning problem, and the rest of the queues are empty. And what we do is that we take this under demanded queue, the yellow vertex here, and we simply hang this component from the root. Then forming the static priority order becomes fairly simple. Farther a match from the root, higher its assigned priority. So in this example, these numbers next to the match values give us one possible way to come up with the priority orders. So match 1 has the highest priority, and then match 5, and so on. So I think I'm almost out of time, so let me briefly conclude the talk. So hindsight optimality is a natural lens to capture this tension between short and long-term objectives. And we established that it's possible at all times to generate the same total value as no-regret planner up to a constant, where this constant does not grow with time. And then we characterize the optimal scaling for this constant regret by the general position gap epsilon. And this performance is achieved by simple batching and greedy policies that we proposed. And for me, these are the main messages of our work. So theoretically, knowledge of basic feasible activities is very powerful. And that is, studying the deterministic counterpart of your dynamic system is important in designing your policies. And long story short, what we are saying is that in multi-way networks, a small delay is required. But surprisingly, in two-way networks, there's no need to wait at all. And practically, our results speak to the concerns that matching frequently may harm efficiency in matching systems. And I think it's nice to have greedy policies with strong performance guarantees that are local and simple. And other than forming the static planning problem, you don't require additional optimization. So thank you very much for listening to my talk. I'm happy to answer any questions.
Thanks, Süleyman. So we probably have time for 1 or 2 questions. All right. So we don't have any more questions. Let's thank the speaker again.
Thank you.
So our third speaker is Yegane Ali Mohammadi, and she's going to tell us about the value of excess supply in a spatial matching market, which is a joint work with Mohammad Akbarpur, Sheng Wuli, and Amin Saberi. So the floor is yours.